right, so hopefully at this stage you've worked your way through the lecture on linear systems. So the major points there were that we can analyze systems using the Roach-Capelli theorem if our system is in row echelon form, reduced or non-reduced. We can easily identify whether or not the system is consistent by looking for a pivot in the augmented column. If there is a pivot in the augmented column, we're inconsistent. If there's not a pivot in the augmented column, we are consistent. Then we can identify the variables as either dependent variables, those are the variables in pivot columns, or free variables, those are the variables that correspond to non-pivot columns. The Roach-Capelli theorem says that if we are consistent, then we either have only one solution, as long as there are no free variables, or we have infinitely many solutions if there are free variables. So I want to walk you through just two things that I've written here in Sage that might help us with some calculations, or at least help us with analysis. So it's possible to construct augmented matrices in Sage. So the idea here is we could use the syntax matrix.augment, open parentheses, and then type our vector in that we're augmenting with. And the keyword subdivision equals true. We'll put that line in in the rendering of this matrix. So in this box, I've predefined code where I have a matrix on the first line, A, and then I've defined a vector on the second line, B, and there's only one print statement here, and it'll just print out the A augmented by B. So let's look and see what happens when I click evaluate. Great. So I see the matrix that I input, and then now you can see the vertical bar here, and then with the vector that we input. So that vector was 6, -9, 2, 1. So if you want to look at an augmented matrix, that's how you do it. Of course, in class we did a more sophisticated analysis by applying the Roach-Capelli theorem, like I just described. I have that analysis in this cell here. That I had to write some custom code to do this, but I think it works. So the syntax or the inputs are exactly the same as the previous cell. I've input a matrix on the first line and then a vector on the second line. And so the idea is that we're going to augment this matrix with this vector. And then as long as we're in either reduced row echelon form or row echelon form, this code will perform the analysis given by the Roach-Capelli theorem. So let's click evaluate. And here we see the augmented matrix that we've input. We can look at it ourselves and see that we are in row echelon form, but we're not reduced. So there's a row of zeros at the bottom here. We have pivots here, here, and here. So those pivots are 2, 3, and -4. We don't have a pivot in the augmented column, so the system is consistent, and that's given to us here. Is the system consistent? The answer is true, meaning that the system is consistent. Now, note that how many variables are in the system? Well, how many columns are in the coefficient matrix? 1, 2, 3, 4, 5. So there are 5 columns in the coefficient matrix. However, we only have 1, 2, 3 pivots. So we should have 3 dependent variables and then 2 free variables. And indeed, our code here is telling us that the dependent variables in the system are the first, second, and fourth variables, and the free variables are the third and fifth variables. And of course, because we're consistent and we have free variables, we now know that the number of solutions is infinitely many. The last thing I'll mention here is that this code will only run, I think, if we are in reduced or are in row echelon form at least. So if we put in something that's not in row echelon form, so if I change like the last row of this matrix to just have a bunch of numbers here, if we click evaluate, the code will throw an error because I input something that's not in row echelon form. In the next lecture, we'll learn how to take something ugly that's not reduced and transform it into something in reduced row echelon form so we can apply our analysis here to write down the solutions to the system.